Lab 5, Own Adventure. For this fifth video lab report, we were able to analyze our own adventure, our own interesting experiment. We were presented with some options and we were given the chance to choose between analyzing such choices or analyzing a different one. I decided to analyze one of the options, Felix Baumgartner's jump from the stratosphere by Red Bull. His jump was done with the attempt of breaking the speed of sound, and it started from a balloon that was 120,000 feet above the Earth's surface. For this lab report, I created a code to predict Felix Baumgartner's position after 60 seconds of freefall using Newton's second law. This prediction was done based on the initial conditions we knew. This will be stated in a few moments. According to the actual data we have, Felix reached supersonic velocity after 34 seconds he had been free-falling, and his location then was 33,446 meters. After 60 seconds of freefall, he reached a velocity of 1,043 kilometers per hour, which is 290 meters per second, and his position was about 23,000 meters. This is not really close to our predictions, but we'll discuss the specific results as this video goes on. Based on the velocities proportioned in the official webpage of the ACT, Red Bull Stratos, the internal energy was calculated for Felix, and this data will be given as the video goes on. Finally, based on our model, Felix would have had to jump from a higher distance to reach supersonic velocity in free fall. Let's proceed to the analysis of the actual lab, starting by the initial conditions used. Felix's mass as a whole is 103 kilograms. This includes the special suit he used, which is 25 kilograms. He starts from a distance of 37,000 meters above the surface of the Earth, which is equal to 120,000 feet. We know that Felix was on free fall for 4 minutes and 20 seconds, and this will help us define the amount of time our loop will run. As established in the introduction, the loop uses Newton's second law as the fundamental principle to predict motion. Now, to use Newton's second law, we must determine the forces acting on our system, Felix. These include the force exerted by the Earth, the weight, and the drag force, which is determined to be a constant b times the velocity squared times j hat, which establishes that the positive y-axis points to the top. In the real jump, Felix first started to fall with gravity being the only force acting, and as the velocity increased, the drag force increased, until Felix reached a terminal velocity, a constant velocity, meaning that the net forces were equal to zero, so the drag force was came to be equal to the weight. Knowing all this, we can create a while loop in our code to simulate what's happening. Let's take a look at the code running. As you can see, the object, or Felix, is so fast that we can barely see it coming down. The graph creates the right curve. It symbolizes the fact that at the beginning, Felix's velocity was increasing in a higher rate, yet as the velocity increased, the drag force came to play to slow him down. According to our model, when 60 seconds of free fall have passed, Felix has only moved about 7,000 meters, while the actual movement he made was 13,000 meters. This may be due to the fact that the drag force changes along his track. The drag force or air resistance might change for several reasons. These include the fact that he starts out in the stratosphere, where the density of the air and the temperature change with altitude. Another reason why our model might be wrong is the weight force we used done by the Earth on our system. Because of the altitude Felix has when he starts free falling, it might have been better to use the force of gravity done by the surroundings on our system, symbolized by the formula constant g times the mass of one object times the mass of the second object, all divided by the square of the displacement. Finally, I'd like to talk about the energy principle applied to this specific problem. Taking everything as our system, we know that delta E is equal to 0. It is also equal to the change in kinetic energy plus the change in gravitational potential energy due to the Earth plus the change in internal energy. From that and plugging in our values, we get that Felix's temperature increases as he keeps free falling. Overall, it is important to conclude by saying that this problem was hard to model and predict in Python because of the fact that the surroundings undergo certain changes while the system moves. It would have probably been better to start the problem from a different fundamental physics principle, the energy principle, Yet it was very useful to analyze it using Newton's second law for all the drawn conclusions. Let's finish up this fifth video lab report by watching the moment when Felix Baumgartner jumps off from the stratosphere. It's pretty impressive.
That's really high. How small you are. I'm going home now. Jump away.
Thank you.